This video is on Descartes' rule of signs, and the basis of this rule is that it's supposed to help us eliminate some possible rational zeros. You know, when you make your list of your possible rational zeros, all those numbers that you have to check with the synthetic division, this Descartes rule of signs is supposed to help us eliminate certain choices. So let's take a look and see how it works. It says, given a polynomial in descending order, the number of positive real zeros equals the number of sign changes in the function. We'll forget about this part for right now. So what we have to do is go through here and just look at the number of sign changes. Starting right here, that is a positive 3. So this changed from positive to negative. That's one sign change. This went negative next to negative. That is not a sign change. This is a negative next to a positive. That is another sign change. This is a positive next to a positive. That is not a sign change, but a positive next to a negative. That is another sign change. There are 3 sign changes. That means there are 3 positive real roots, or, let's look at that second part, the number of sign changes reduced by an even number. Well, I can reduce 3 by 2 and get 1. Wouldn't help me any to try to reduce 3 by 4 because that would give me a negative number. So what this says is that this polynomial has 3 or 1 positive real roots. That does not help us a whole lot because real also includes the irrationals. You know, we could have 2 plus radical 5 being one of our roots, and we'd never guess that. That wouldn't be in our list of possible rational roots. So this is an example where using Descartes' rule of signs really doesn't help us in the grand scheme of things. But you still need to learn how to use the rule. Here's a new polynomial. Let's see if we can find the number of sign changes. Remember to start at the beginning. That is a positive. Positive next to negative, that's one change. A negative next to positive, that's another change. A positive next to negative, that's another change. Negative next to positive, that's another change. And positive next to negative, that's going to also give me a change. So that's 5 sign changes. That means there are either 5 positive real roots, or reduce that by 2, gets us down to 3. We can reduce that by 2 again, gets us down to 1. So for this polynomial, which is x to the 7th, which is going to have 7 roots, then there are 5 or 3 or 1 positive real roots. Not real helpful when we go to do the synthetic division. Take a look at this one. This is positive. Positive next to positive, that's not a sign change. But positive next to negative, that is a sign change. Negative next to positive, that is a sign change. Positive next to positive, that is not a change. There are 2 sign changes. Therefore, there are 2 positive real roots, or there are no positive real roots. Still doesn't help any. Negative next to negative is not a sign change. Negative next to positive is. Positive next to positive is not a sign change. There is 1 sign change. There is 1 positive real root. And you might think, oh, that's going to be very helpful, but it's real. It could be a radical, so it doesn't help. So you're saying, if this doesn't help us, why are we doing this? Well, there is one circumstance where this is helpful. Take a look at this function. This is a positive. Positive next to positive, there's no sign change. Positive next to positive, no sign change, etc. There is no sign change anywhere. So there are 0 sign changes. That means there are 0 positive real roots. So that when we would make our list of possible rational roots, 1, 2, 4, the reason we're just looking at the back number is because the coefficient here is 1. We ordinarily would say plus or minus, meaning there'd be 6 things we'd have to try. But since this has said there's no positive real roots, instead of having a plus or minus here, I would put a minus in front of all this. So I would need to check -1, -2, -4. So in this instance, this has cut my possible rational roots in half. This is the time Descartes' rule of signs is helpful. Let's finish out this problem. Let's do -1. -1 times 1 is -1. Add those and get 1. -1 times 1 is -1, gives me 4. -1 times 4 is -4, gives me 0. And then this is x squared plus x plus 4, which does not factor. We're going to have to use a quadratic formula on this. So this will be -1 plus or minus 1 squared minus 4 times 1 times 4 all over 2 times 1. Doing the arithmetic on this, we're looking at 1 minus 16, which is negative 15 over 2. Remember, the square root of a negative produces an I, so this is negative 1 plus or minus I radical 15 over 2. So one of my zeros was negative 1. It's a negative value. These are imaginary. Actually, these are complex. There's no positive or negative to this. So it does verify the fact that there are no positive real roots. There's also a rule to help us find the number of negative real roots. And it says, given a polynomial in descending order, the number of negative real roots equals the number of sign changes in f of negative x, or is equal to the number of sign changes reduced by the even number. We'll talk about the reduced thing. So what does f of negative x mean? It means we're going to put negative x in for every x. But what does that really do to the function? If you put a negative x in here and raise it to an odd power, it's going to stay negative. Raise a negative to an odd power, it's going to change the sign and go positive. Raise a negative to an even power, it doesn't change. Raise it to an even power, it doesn't change. Put a negative x in here. This is an odd power. This is x to the first. It changes to negative. So that all this does is we're going to take the function as written. I'm just going to wipe all that out. We're going to take the function as written, not worry about this f of negative x business, and just change the sign on any odd power. That's an odd power, change the sign. Odd power, change the sign. Even power, leave it alone. Even power, leave it alone. Odd power, because it is x to the first, change the sign. Now take a look at your sign changes. This is a negative next to a positive, that's a sign change. A positive next to a negative, that's a sign change. Negative next to a positive, that's a sign change. Positive next to negative, that's a sign change. Negative next to negative, that is not a sign change. There are 4 sign changes. Therefore, there are 4 negative real roots, or reduce it by an even number, which means reduce it by 2, or 0. New function, all we're going to do, because we are looking for the number of negative real roots, then we're just going to look at the powers. Odd power, change the sign. Even power, leave it alone. Even power, leave it alone. Odd power, change the sign, and then look for the number of sign changes. Negative next to positive is a sign change. Positive next to negative is a sign change. Negative next to negative, no sign change. Negative next to positive, that is a sign change. So there are 3 sign changes. So there are 3 negative real roots, or 1 negative real root. But remember, that real could be a radical. Let's go through here, change our signs. That's an odd, change the sign. Even, leave it alone. Odd, change the sign. We have positive next to negative, that's a sign change. Negative next to negative is not a sign change. Negative next to positive is a sign change. There are 2 sign changes, therefore there are 2 negative real roots, or there are 0 negative real roots. I haven't explained to you yet why we need to reduce our number of roots by 2 or 4, etc. And it's this idea. Whenever you have complex solutions, they occur in what's called conjugate pairs. If you think back to the one problem that we actually did all the way through in this video, we found -1 initially, and then we had to use the quadratic formula and find these roots, -1 plus or minus I radical 15 over 2. The plus or minus is supplying 2 solutions. And that's why we have to reduce our number of roots by 2. Could be by 4. If we had something huge like x to the 5th power, we might have 1 real, and we might have 4 complex. 2 of them would be one pair, 2 of them would be another pair of complex conjugates. So that's why we have to also do this reducing by an even number thing to get multiple answers on these.